thank you so much, Enrique, for the invitation to Erlangen. This is actually my first time in Erlangen, and I was really delighted to be reminded, actually, that Emmy Noether was born here and studied here. And Noether's theorem is actually one of my favorite theorems. I'm a physicist, by the way, my background. And of course, Noether's theorem, as you know, it's a beautiful way of seeing how mathematics actually impacts, something so deep in physics, like symmetry and conservation. And what I'm doing now is, quantum computation. Actually, this is another example of where, having a physicist's way of interpreting the world, it really helps us, rethink what we mean by algorithms. Okay, so you guys, I'm sure most of you know much more about PDEs than me. Okay, so I work with Professor Jing, who's an expert on PDEs, and some of our other collaborators. But what about the quantum simulation? Okay, part of this talk. Okay, so what we really mean by that is actually what happens when your computer itself, right, actually obeys quantum dynamics and not classical dynamics. And the information now is embedded inside your quantum states. Okay, and now when we think about, simulating, okay, PDEs, beyond Schrödinger's equation, right, then we also need to modify the way we think about algorithms. And I'll show you how we've been doing this in recent years. So I don't need to explain MODs or PDEs to you guys, okay, and their importance in scientific computing. But what we'll do say is that, as you very well know, okay, in classical numerical algorithms, a big problem is the cursor dimensionality. Okay, so the higher dimension, okay, it becomes exponentially more difficult. But what we do know is that if, a particularly good example of that is, say, n-body Schrödinger equations. Okay, when you have, high dimensional equations, it becomes exponentially more difficult. And this is when, people like Paul Benioff and later Feynman suggested, well, what happens if you want to simulate, okay, Schrödinger's equations on actually a quantum device itself, that itself obeys Schrödinger's dynamics. And there you can actually alleviate the cursor dimensionality, all right? And now we think, well, Schrödinger's PDE, that's just one particular PDE. What about all these other PDEs that everyone's interested in? Okay, so maybe, if we can map these onto Schrödinger-like equations and put them on a real quantum device, we can also help alleviate the cursor dimensionality for those problems as well. Okay, so therefore the very first step, to do that, is to actually do this mapping. Okay, how do you turn non-Schrödinger-like equations into Schrödinger-like equations? And this is something that we call Schrödingerization. Okay, and the name I think is self-explanatory, and we'll introduce these a bit later on. But and since I have an idea that you guys are mostly classical, numerical methods and classical machine learning, I'll just say, give a little bit of background on quantum computing, okay, and what we mean by quantum simulation. So here, I talk about, obviating the cursor dimensionality, and this is really saving on time complexity. Okay, or the time steps. But actually, if you want to go beyond classical infrastructure and use quantum devices, it can also help with other things, like memory, energy cost, communication, and so on, which I won't talk about. But also the fact that it's inevitable, okay, because as our chips get smaller and smaller and smaller and smaller, they will hit the quantum scale. Okay, and they'll no longer obey purely classical laws. Okay, so you can't have these, circuit equations that work in the same way. Okay, so it's really inevitable. So then you guys are mathematicians saying, okay, well, this is an inevitable future reality, okay, that we really have to, confront quantum mechanics in one way or another. How do we think about algorithms? And this is some, key message that I want to, present here is that now, the computational techniques and methods that, people have been doing, for the last 40, 50 years, we really have to rethink that because the actual infrastructure in which, the computation is based on, that changes. And therefore, even the mathematical language that we use, that also has to be modified. And I'll give you some examples of that today. And just for those of you who haven't, seen Schrödinger's, we actually saw this in the previous talk, but this is Schrödinger's equation and evolves by unitary evolution. Okay, and the chief behavior of that is dominated by the Hamiltonian H, okay, which is a Hermitian operator. Okay, so what do we mean by quantum simulation? Okay, why is it a hard problem? So what we mean by that is that if you, start off with, a quantum system, at time t equals to 0, and then you want to ask the question, well, what is the state after a certain amount of time t? Okay, what happens? So if you have a system that's made up of quantum bits, and I'll introduce that a little bit more later, but you can think about these as two-level, systems, If you have n two-level systems, how do you predict what happens? So if they obey Schrödinger's equation, now even to represent the information of these n two-level systems, you need classical entry of 2 to the power of n. So purely memory. But now dynamics, now a Hamiltonian, dynamics, now that's 2 to the power of n by 2 to the power of n. So even to process that becomes exponentially more difficult. And actually today already we're reaching the limit of what classical devices can simulate. So on the order of hundreds, but now we already know on real quantum systems we can actually go beyond that. And I'll also introduce something today what we call continuous variable quantum modes, and for that you can go into millions. And we're actually doing some experiments related to these. So I'll introduce the language first. And there are two types of quantum information I like to talk about. One is something you probably would have heard of, which is quantum bits. Now, everyone is familiar with bits, zeros and ones, and all your numerical algorithms are really reduced to bits, in the end. But why do we work with bits? That's actually deeply related to physics, because information doesn't exist by itself. It has to exist in a physical substrate, and the way that the physical substrate represents that information. So when Turing presented his model, so you have a tape, and you have holes that are punched or not punched. So that's 0 or 1. But you can't have stuff that's in between, like a half-punched hole. So we don't have that in Turing's model. But now instead of using tapes with or transistors on and off, so instead of using these systems to represent information, what happens when we use, for example, atoms to represent information? So one way that we can use atoms to represent information is, for example, energy level. Your ground state, your lowest energy state, and your first excited state. You can say, well, lowest ground state, that's 0. First excited state, that's 1. But it turns out that in physics, you can have states that's not either 0 or 1. And in physics language, we call this a superposition, but it's really not equivalent to a mixture. It's not like like a probabilistic coin. Like half the time it's tails or half the time it's heads, and it's very difficult to actually explain, right? Because evolution hasn't equipped our minds to deal with this. So it's much better to think about it abstractly, mathematically, that we actually represent these states in complex Hilbert space. So for a single qubit, you can think about the x-axis, going as the ground state, the y-axis as the first excited state, and most states, is a vector in this space. And what do the components alpha and beta mean? Well, the absolute squared value of that represents the probability, right, that you observe, right, your atom either in the ground state or the first excited state with that probability. And then if you have, multiple, say n qubits, then, it's in 2 to the power of n dimensional Hilbert space. But the mathematical language, right, that we use here are vectors and matrices. So Schrödinger's equation is linear, so we can use linear algebra, and therefore, all we have are matrices. And the way that we represent dynamics, again, is using matrices, how you transform one finite dimensional vector into another finite dimensional vector, with matrices. And we can represent these, again, by, sums of Pauli operators. And, we can represent them in lots of physical systems, ion spin systems, superconducting qubits, and so on. So that's information, right? And I said the dynamics you can represent by matrices. But if we want digital evolution, and this is, analogous what we do classically, is that we concatenate, right, our evolution into a lot of steps. So if we have universal devices, this is what we can do. And if we have a fully digital, programmable, universal quantum device, then we can really use it to represent any unitary matrix. So long as we have smaller systems, so the smaller gates, and we can always compose them into any unitary gate. Now, however, to actually realize this, and in a fault-tolerant way, this is kind of not near-term, So we really have to wait a while. We actually don't know exactly how long we need to wait before we do something reasonable. And certainly, if we want to simulate something like ODs and PDs, we're really not there yet, On the other hand, physics actually provides us with systems which are called continuous variable, quantum systems. And in fact, in quantum computation, people don't mention this very much because a lot of them, they come from computer science, actually in computer science from the Turing model, okay? So they're very biased towards discrete systems. But as a physicist, right, we know that most continuous systems, most physical systems are indeed described in a continuous way. And indeed, the PDEs that you guys work with, they're inspired by nature, they're continuous. Okay, and indeed, there's continuous quantum information, and for those of you who might have heard of like wave function, and actually this is the representation, okay, in terms of wave functions, and here you can think about this as really living in infinite dimensional, okay, Hilbert space, and this x here you can think about as position, and we know that things like position and momentum, okay, so these are all continuous quantities, okay. So now what are the operators? Okay, so before we had matrices, okay, so that language, but now because we're living in infinite dimensional space, we need to use operator language. And again, this is different mathematics. And there are two key operators I want to introduce. So we have what we call like x hat, so this is a position operator, and he acts on a position eigenstate that reproduces for you, the position. Okay, and P represents momentum. And if we and this is important for us later, that if you want to represent, okay, what happens when you multiply, okay, your wave function u of x by x, then you act upon that state by a position operator. But if you want its derivative, okay, then you multiply that, then you actually take a derivative, okay, of that function. So x goes to x hat, okay, and ddx goes to I p hat, okay, where I is your imaginary number. And another really important property to look at is that if we look at the inner product between the eigenstates of position and momentum, what do we notice, right? It's e to the power of ixp. And this is really what we see when we do Fourier transforms. Okay, so this is a factor that's involved. And this will also be important for us later, because it turns out that actually in most powerful quantum algorithms, you actually need to do Fourier transforms and inverse Fourier transforms, right? And if you want to do these on qubit-based systems, it's actually very, very difficult to do. But here, we actually see it's actually really very natural, because what you're doing is that you're just transforming a basis between a position basis to a momentum basis. So it's like your measuring instrument. If you won't measure momentum, you could be measuring position. And just by making this change, you're actually doing a Fourier transform. Okay, so this is very easy to do for things like on optical systems. And this will also be important for us later. Here, okay, so these continuous variable systems are represented by things like lasers. I don't have a laser pointer today, but I usually do this with a laser pointer. Okay, so the state that comes out of a laser, okay, that's directly continuous variable, quantum state. Okay, you have light inside cavities, or you have freely moving atoms, and so on. Okay, and now what about evolution? So before we talked about discrete evolution, breaking up into lots of, gates, and I said we're really far away from, realizing that. On a real quantum device. However, all quantum systems that we know, including you and me, okay, we evolve through continuous time. Okay, so if we have time evolution through continuous time, this is very relevant for you guys who study control, right? Because it means that if we're able to find, use control theory to find the appropriate parameters of the Hamiltonian, right, to engineer the final state that we want, then we've actually solved our problem. Okay, so we don't need to go through, doing these universal quantum devices, but specialized devices where you simply control certain parameters. Okay, using control. And again, we have lots of quantum systems that do that too. Like naturally, they're already there in the labs, and they don't, they're not special quantum computers. Okay, that you hear about that Google has and so on. They're just natural in the lab. Everybody already has them. Okay, so. For all these kinds of computing, okay, so we have discrete and continuous ways of encoding information, either in quantum bits or in these quantum modes, okay, or Q modes, or in the processing itself, we can either have discrete time, okay, chop it up into lots of gates, or continuous time. And mostly what I'll be talking about today is the right bottom corner, okay, and this is what we call quantum analog computing. And it turns out the method that we have, Schrödingerization, is particularly suitable, right, for quantum analog computing. Of course, it can also be suitable for discrete computing, but in this technique, no other method can do this, okay, except ours right now. Okay, and just to give you a taste of how powerful quantum modes, okay, these Q modes are, if you, because most people haven't heard of these, is that, okay, so if we think about the poster child for quantum algorithms, Shor's algorithm. Okay, so this is about breaking RSA. Okay, so we know to factor a very large, number n, on a classical device. Okay, it's very difficult, but for quantum algorithms, you can have a polylog n, okay, type of algorithm. So classically, to break the current RSA encryption would take longer than the lifetime of the universe. But if you use a quantum device, okay, even though it won't take so long, but you actually need a lot of qubits, okay, a lot of quantum bits. And this is work I did many years ago, we call this the power 1 QMoD, okay, model. And this is where you can actually replace all these perfect non-noisy, okay, quantum bits in the original Shor's algorithm with a single QMoD. And that is already sufficient for factoring. But of course you say, well, why haven't people done this? Well, it turns out you have to actually exchange number of qubits with the energy required, okay, in a QMoD. But at least this gives you a basic idea, because after all, a single quantum mode is really an infinite dimensional quantum system. All right, so now to our question of how to simulate classical ODEs and PDEs, okay, with quantum devices, how to do the transformation. Well, first of all, we have two types. One is we have a system of ordinary differential equations, or we have, a d+1 dimensional partial differential equation. Okay, and quantum systems or Schrödinger's equation can also have one of these two types. So what we really want to do is we want to map, okay, these guys onto these Schrödinger type equations. Okay, so if you have a system of d ordinary differential equations, then you really want to map to the left-hand side. Okay, where now your Hamiltonian is now in this matrix language. Okay, it's finite dimensional matrix, and then you have a log d size system. Okay. But if you want to simulate a d+1 dimensional PDE, then you really want to map on to a Schrödinger equation, something like the right-hand side. Okay, and now. And this is how Schrödinger's equation is normally introduced. Okay, you have momentum operators, you remember? Okay, so if you remember the rule, and you have the potential, and you remember the rule, when you have a derivative, it goes to IP hat. Okay, and this is what happens when you have a Laplacian. Okay, in your Schrödinger equation, it goes to momentum squared. And this you guys will probably remember from high school, like in physics, right? What do we mean by energy? Because Hamiltonian represents energy. You have kinetic energy plus potential energy. And what is kinetic energy? Okay, that's basically momentum squared. Okay, so all that should fit with the classical intuition, and so therefore what you see is that in system of ordinary differential equations is more suitable to represented by discrete systems. Okay, meaning qubit systems. But if you want to simulate partial differential equations, then you really want to use these QMoDs. Okay, because now these act on infinite dimensional systems. Okay. All right. And when I talk about analog devices now with quantum, okay, simulation, we can have analog, okay, what we said before, and we can also have digital. And just as classical cases, we have digital, and this is where we have this cursor dimensionality problem. But we can also have classical analog devices, which all you guys are probably too young to remember, okay. But yeah, they did have those. But with classical analog devices, they actually don't solve PDEs very well because you have to discretize, okay, your PDEs. Okay. But it turns out for the quantum case, I'll show you later, we don't have to do any discretization at all. Okay, we actually preserve the continuity, right, of the PDE, and that's actually because we utilize quantum entanglement, and then that's another quantum property. Okay, and we actually showed that the quantum cost is linear in dimension, and no discretization is necessary. And we can also use this method to, map it onto qubit, dynamics as well. And again, that would be polynomial, okay, in dimension, and also logarithmic in, the discretization size, okay, of the system. Okay. So the basic idea, or when I say, so this is Schrödingerization, okay, work. So we have the, qubit-based algorithms as well as the continuous algorithms, and I think I'll present the analog form, okay, for you, because I think it's cleaner, okay, to see, and we can always discretize that, okay, later if we want. Okay, so now let's have a look at the original Schrödinger type of equation, and now let's look at a more classically motivated equation like the heat equation. Okay, so what do we notice about these two equations? They basically look the same, right? Right, except there's an I. Right? So, everything else is really the same, and you're like, oh, it's so close, right? So mathematically, what can we do? And of course, people say, well, oh, it's very obvious. It was just an I, right? Let's just get rid of that I. We take I to the left-hand side and make time imaginary. And this is what people did, okay? So this is called imaginary time evolution, sometimes called Wick rotation, okay, for physicists. But now the problem is that in imaginary time evolution solution in time t does not actually correspond to the solution of the heat equation at that time t, because it's not a real time. And in fact, if you want to do quantum algorithms with that, you actually need to do partial tomography at every step, okay, before you know what evolution, okay, you want to perform. Okay. So this is actually I think not a good method, okay, even though mathematically you just do, t goes to it. So now our question is there a real-time, okay, way of making a non-Schrodinger equation Schrodinger-like? Okay. All right, and then, but before we go on, just by looking at this, okay, we're saying, okay, if t goes to it can solve the problem. And when we think about I going to the imaginary, Argand plane, we also think about going to an extra dimension by introducing this I. Okay, so already in your head, you're like, actually, it suggests by adding a dimension, somehow this might help us. Okay, because this is what's happening with this imaginary time. But here, instead of adding, an imaginary extra dimension, okay, or coming from, the Argand plane, here we're introducing a real, okay, extra dimension, and we introduce a transformation that we call the warped phase transformation. Okay, so now we have the heat equation, okay, that solves, t of x, but now let's introduce a new spatial dimension psi. Okay. And when psi is above 0, we multiply, okay, this u by e to the power of minus psi. And this is the warp factor, okay, along this extra dimension. And you're like, well, what's the point of that? Let's see what equation W obeys. Okay. And it turns out this W obeys something, this heat equation in phase space. Okay. So it basically kind of looks like the heat equation, right? Except now on the right-hand side, instead of acting on W, it acts on the first derivative of W, okay, with respect to psi. Okay, and you're saying, well, now you're just making things more complicated, okay? But let's think back to our original question, which is how do we get an extra I, okay, in a real way, okay? Well, because now this is an extra derivative, okay, of W with respect to psi and not, W itself, we can have a way of getting an I if we take a Fourier transform, right? Because if we ever take a Fourier transform and take a derivative, this is how we get an extra I, okay? And this is what we can do, okay? So we have a Fourier transform in this extra dimension psi, and then we take the derivative, okay? Then we get an extra factor of I eta, where eta is a Fourier mode, okay, just psi at. So now what we get in blue, this is really a Schrodinger-like equation now. Okay, so this is Schrödinger's equation for each Fourier mode, and now t you can think about as being dilated by a real number, okay, eta, okay, instead of by imaginary, okay, number. So here you're saying, okay, well, this is like having an infinite number of Schrödinger's equations, right? So how do we actually represent this in a real system? Well, it turns out it's actually very easy to represent this in a real system, even though it's an infinite number of Schrödinger's equations. But remember, a single quantum mode that can be represented by, say, a single laser beam, that itself is already infinite dimensional. So it really means that in a physical system, all we need to do is to add an extra mode, okay? And that can actually capture, having this infinite eta, okay? So remember the rule, okay? Whenever you have, your x, it goes to x hat. Now, eta is actually acting as a spatial mode, okay? So it can go to eta hat, and when you have a derivative, it goes to momentum, okay? So then, this heat equation system really transforms to a Schrödinger system with the Hamiltonian that actually the first part, okay, it looks just like our, kinetic energy plus our potential energy, okay, p squared plus v of x. But now a tensor product, because now we added a mode, has a tensor product of eta hat, okay, acting on this extra mode. Okay, so now this is telling us if we have a quantum system that has this Hamiltonian, then we're actually able to simulate the heat equation, okay, using a quantum device. Okay. And this general methodology works for any linear PDs, but so also inhomogeneous ones and so on. But it's a little bit complicated. So I'll just explain the general methodology for simplicity. Okay, for a linear homogeneous PD, that's first derivative. Okay, in time. So remember the rule. Okay, you can rewrite all these equations as, du dt equals to minus IA of u, where whenever you have x, gets promoted to an operator, x hat. When you have a derivative, okay, then it gets promoted into a momentum operator. So you end up with an operator A, okay, that's made up of, momentum operators and position operators. Okay, so, but with any of these operators, it can be very easily separated into a completely Hermitian form and a completely anti-Hermitian form, right? So if A is completely Hermitian, that's just your regular Schrödinger-like equation. If it's completely anti-Hermitian, that's exactly like your heat-like equation, okay? So, but if it's anything between, okay, then any operator A can be written as a sum, okay, A1, which is Hermitian, minus I A2, where A2 is also Hermitian, okay, where A1 is just a sum of A plus A dagger, and A2 is just A minus A dagger, okay, well, with an I. So then the Hamiltonian that we have is, I don't have a pointer, but if you can see, it's equal to A2 tensor product eta, and that part I already saw before with the heat equation, okay? This is the completely anti-Hermitian part, tensor product with our eta hat, okay? Plus A1, which is a completely Hermitian part of the equation, tensor product, the identity, right? And why does it have this form? So if you remember, if you have something that is completely heat-like, okay, so the opposite of Schrödinger's equation, okay, in a sense, then you have to utilize your extra mode, okay? And in fact, having this tensor product actually implies there's entanglement, okay, between these modes. But if your operator has the completely Hermitian part, which is A1, that means it's already Schrödinger-like. So you actually don't need the second mode, and that's why it's tensor product identity, okay, because you actually don't need to utilize this extra dimension. So in a physical system, if you have access to a Hamiltonian of this form, then you can actually simulate differential equations, okay, of this form. Okay, so as an example, if we have a very high dimensional Fokker-Planck equation, and if you have an example of linear drift and additive noise, then we have the Hamiltonian on the bottom right-hand side. And actually, if you're a physicist and you see this, you're actually saying, actually, this looks very familiar. Okay. So for the second part of this term, this is something that people see all the time in linear optical systems. Okay. Now the first part of this Hamiltonian is a little bit trickier, that there are parts of it that can be seen in superconducting systems, okay, and that there are actually transformations we do to make it even easier. So we are actually currently conducting experiments to actually simulate, okay, equations of these form. Okay, so sort of the summary, okay, it's actually incredibly easy to do. If you have any linear system of ODs and PDs, okay, you find out the completely Hermitian and anti-Hermitian, okay, parts of your operator A, right? And if you want to simulate this on a quantum device, what do? You find a Hamiltonian of the form A2 tensor product eta hat or x hat, okay, same thing, plus A1 tensor product the identity, okay, and you can go back and forth. Okay, and because everything is kind of linearly related, it's very simple to do. Okay? And if you want, you can also simulate this on qubit-based systems. So you can have a qubit representation of x hat, which is a diagonal matrix. Okay, from minus n to n, when n is your discretization size. Okay. And this is again like another flowchart. Okay, of what you can do, and this is also applicable when you have time dependent Hamiltonians. Okay, as well. Okay, and here you can see it's very easy to go back and forth. And for those of you interested in saying, well, what does it actually look like, okay, on a device? Well, what do you need to do? Well, what we need to do is that we need to prepare, okay, the initial condition of our system in a quantum state. And remember, we have this extra mode, okay? So we actually need to prepare the initial condition of this extra mode, and it's actually related to applying the warped phase transformation. We need to, multiply things by e to the power of minus psi. But it turns out, so that turns out that, it's good to prepare a quantum state, okay, of the form above, so the integral of e to the power of minus psi. But it turns out that this state is actually very, very close to a state that directly comes out of your laser, okay, what we call a coherent Gaussian state. Okay, it's very, very close. So experimentally, this is what we're using. And in the end, to actually find the answer to our problem, okay, we need to make a measurement just on our extra mode. Okay, so if we measure momentum, okay, so long as our detector says momentum's above 0, okay, then we can be guaranteed we have the solution to our problem. And if we have a d-dimensional linear PDE, then here all we need are d+1 dimensional quantum modes. Okay? And as I said before, actually in linear optical systems, d can actually get up to 1 million. Okay, so this is like a 1 million dimensional PDE. Okay, so just a summary. Okay, if we have d-dimensional like PDE, if we want to simulate this with analog quantum devices, then the quantum cost is linear. Okay, in dimension. And we don't need to discretize anything, okay? We didn't do any numerical tricks, okay? This is exact mapping. If we have, I didn't show this, but we could also map this onto qubit-based systems, okay? And in many cases, these can also be efficient. But whereas classically, we see they either have the curse of dimensionality or you're really forced to do a discretization. Okay, and where is the quantum, okay, part in all of this? So this is actually important also for foundational type questions because we can actually see it's so easy to map any linear PDE into our quantum system. We can actually see which parts of the PDE, okay, visual PDE, maps to which part of the Hamiltonian. And this is something that you cannot see if you discretize and scramble everything up into lots of gates because all the structure of the PDE is completely destroyed. Okay, we can't, see that. But here it's very, very clear. And what we do know is that in quantum systems, for example, in continuous variable quantum systems, there are certain types of gates which that may not be classically simulable. Okay, and we know that some which are. So we can actually see which type of PDEs are in fact classically simulable, even though we're performing on a quantum device, and which ones are likely maybe not so. All right, so like this little summary table. So we have lots of examples of PDEs that we can do: the Liouville equation, heat equation, Fokker-Planck, Black-Scholes, a wave equation, and Maxwell's equation, okay, and so on. And we can also apply to lots of different boundary conditions and so on. And I don't say here, but we can also use this for linear algebra problems. Okay, preparation of ground states, which is important for optimization problems, and preparation of thermal states, which is actually important in machine learning. Okay, if we think about quantum and Boltzmann machines and so on for generative learning. Okay, so there are also lots of applications there. Okay, and there are a lot of benefits. Okay, to this. Because here, as you see, we take advantage of this exact mapping so that we don't need to perform any discretization. Okay? And we have real quantum systems that naturally are continuous. Okay? So we can have good specialized devices, right, that can simulate these PDEs without resorting to universal quantum devices before they're available. Okay? We don't need to discretize in time. Okay? But also the formalism is flexible enough that if you want to use qubits, you can. Okay? If you want. And in fact, we're developing a software that allows you to it's a dedicated for PDE, like using our method for simulating PDEs on classical devices. Well, it's really simulating the quantum dynamics on classical devices. Okay, so and here we can use discretization, and it avoids a lot of the complications also of techniques that you'll be familiar with in classical numerical methods. Like if you want to use matrix inversion methods, then you need to know condition numbers and all of that, blah blah blah. But here we don't need to worry about that if we stick with a continuous formalism. And again, the cost is in D in terms of number of modes, not exponential, okay, in D. Okay, and again, there are lots of opportunity for more foundational exploration on what is quantum and what is not. Okay, all right. So since I have some time, as well, so as I talked about here with Schrödingerization, okay, so where we added one dimension into our classical system, and now we can actually use quantum dynamics to simulate this classical dynamics. But we have other tricks, okay, as well, where adding a dimension really helps, okay, so that problems become simpler by lifting to a high dimension. Okay, because remember that in quantum simulation, okay, because we don't have this curse of dimensionality issue in the same way. So if you're adding, k extra dimensions, you don't need to have an exponential cost in k, okay, that you would need to pay classically. So we have, other tricks that we use, okay, but adding this extra dimension include if we have non-autonomous systems, we actually show how linear non-autonomous systems can become linear autonomous systems, okay, by adding an extra dimension, or maximum 2, okay, but for quantum systems 1. And also, if we wanted to do uncertainty like uncertain problems, uncertain PDs, by adding some extra dimensions, we can actually make them deterministic problems. Okay, and for certain types of nonlinear problems, okay, or for certain kinds of nonlinear PDs, by adding some dimensions, we can actually make them completely linear and then solve for these. Okay, as well. So again, all these methods of increasing the dimension, now they can make the problem simpler, but classically you have to pay this exponential cost. But now if we can map them onto the quantum system, we don't. Okay, so that allows us to use these tricks. Okay, so this is the idea. Okay, so like usually, like classically, you want to turn a high dimensional problem into a low dimensional problem. Okay, but for quantum, we have a little bit of a leadway where we can have a few extra dimensional problems without too much extra cost quantum mechanically, so we can kind of go the other way. Okay, so how to turn low dimensional problems into one that's slightly high dimensional, okay, to make our lives a bit easier. So one of these methods is, for non-autonomous PDs, how do we turn linear non-autonomous PDs into linear autonomous PDs? Okay, and I think this is also an interesting trick, classically, and this is really about adding an extra clock. Okay, so for example, we have quantum dynamics on the left-hand side, which is non-autonomous. So your Hamiltonian is dependent on time. What you can do is that you can add an extra dimension. Okay, we can call S, which acts as like a clock. Okay, so and in fact, when you think about what time is, okay, there's no actual time dimension. It's like the way that we represent time is always through space. Okay, if you're looking at an analog clock right there, that's using angular degrees, spatial degrees of freedom to represent time. Okay, if you're looking at a digital clock, that's, again, digital spatial degrees of freedom. Okay, and this is really captured here, where you use S as a continuous clock where, the position, okay, along the, so if you're reading the position, okay, along the clock, that's actually telling you the time. And you need to tell the system that you're actually using this, okay, time, that time actually moves, and this is why you have, dWds. Remember, DDS is like a derivative is like momentum, okay, and this is actually telling you as your time goes, it actually shifts. Okay, so by adding one dimension, you're turning the system on the left-hand side into a PD on the right-hand side that looks just like your original, okay, PD, except you're adding a momentum, okay, to this clock. Okay, so this is the dWds, and your time t has become s because it's now transformed into this spatial, okay, degree of freedom. Okay, so this is by adding one extra dimension, and note that this is very different to the way that people normally introduce clocks in here. Okay, so if you introduce it without adding this momentum operation, then you're not really telling the clock what to do. Okay, so in that sense, you're actually solving a coupled system, okay, of your clock ds, your clock system s, as well as your system u. But this coupled system is nonlinear. Okay, but whereas if you tell the clock to move, okay, in your original PD, then it doesn't become a coupled system; it becomes a single PD. Okay, that actually already has your time embedded in there. Okay, and that's why it's linear. All right, so now, so this is by adding one dimension, you turn a time-dependent, a non-autonomous Schrödinger equation, okay, into an autonomous linear equation, okay, in green on the right-hand side. So if we started off then with any linear PD, we know from Schrödingerization, right, that we can actually change into a Schrödinger-like system by adding one dimension. Right? So which means that if you want to map any non-autonomous linear system into an autonomous linear system, maximum you need to add in 2 dimensions. Okay, and that's sufficient. In terms of implementation, it's actually also really simple. Okay, so we prepare the initial condition of our system, and again we have an extra mode, and this extra mode is really our clock. Okay, and we initialize this clock, and and that notation just means we initialize at 0. Okay, of our clock, and then you see the evolutions, e to the minus I h bar t, where now this h bar itself does not depend on time anymore. Okay, so whatever your time dependence was, you're actually changing it to an operator s hat, which is your clock. Okay, but now you have to add in. Okay, so this h bar is h of s hat plus this momentum operator, which now moves. Okay, your time. And in the end, what we do is that with this extra mode, we don't need to make any measurements, we just throw it away. Okay? And after throwing away the state that we have in the end, we can guarantee that to be very close, okay, to the state that we want. Okay? So this is a very simple protocol. okay, for doing this. Yeah, and then we also have some, other methods. Again, seeing how, physics really helps with this. So suppose we want to solve uncertain PDEs. Okay, so what do we do there? So in our PD problem, what we mean by uncertain PDEs, we mean the coefficients of our PDEs are stochastic. Okay, so they depend on stochastic variables, which are sampled from some stochastic distribution. And one way of solving for these is that, you're doing the sampling, okay, so you're getting different coefficients each time. And each time you get a different coefficient, you solve this PDE, but then you need to solve many different PDEs, okay, because each time you have some different coefficients. And then you take some ensemble average, okay, maybe get some statistics from that. But that actually means that if you have to sample many times, or if you have, a very large number of stochastic variables, you need to solve, many different PDEs, okay? And that's not very efficient. Okay, so the question is there a way of directly capturing these ensemble average quantities without solving the PDE so many times? Okay. And there's one really beautiful way, I think, where, physics really comes into this, and this is what we call quantum stochastic Galerka method. Okay. And this is how it works. So suppose we start off with a very simple convection equation, okay, of du dt, where, c of j are, you can think about that as your speed, okay? And your z's are your stochastic coefficients, whereas your x's, that's just space. Okay? And now let's suppose that your stochastic variables, they're sampled from some Gaussian distribution, okay, which is very natural. Okay? So then what we can do is that we can expand our solution u, okay, into a discrete, okay, well, an infinite sum, where little n here are natural numbers, okay, and they're expanded in terms of polynomials, okay, where u of n are the coefficients to the polynomials p of n. And it turns out that if we associate n with particle number, okay, so say if we're, performing an optical experiment to simulate this, and then we associate, these natural numbers n with, the particle number, so meaning that if we're making measurements on these systems, our particle detector, right, is it, turning on when n equals to 0, 1, 2, 3, okay? So if we associate n with that, and if we associate, x with, the position quadratures, then it turns out that the inner product of these actually gives us Hermite polynomials. Okay, so which means that mathematically, if we associate n with this real physical, okay, particle numbers, then just by making particle number measurements, we can actually naturally take into account this Hermite polynomial, okay, way of expanding, okay, our solutions. Okay, so and then it turns out that if we want ensemble average of our solutions, okay, we actually don't need the full set of solutions. So all we need are, the zeroth coefficient, okay, u of 0, okay, of our solution. And to get the variance, we need the variance of, un squared, okay, of these coefficients. But the maximum n doesn't have to be very high, okay, because for, smooth enough functions, n, can go, be 4 or 5. And which means that, physically, when you're making doing an experiment, all you need to do is to, when doing these experiments, when you're making photon number counting measurements, you just need to calculate the probability to which you don't get any photons on one side, okay, and that will tell you the ensemble average. And then you only need to measure up to, photon number up to 4 or 5, and that's enough to actually tell you the variance of your ensemble solution, okay, without you sampling, okay, so many times. So this is one method, okay, for uncertainty quantification. Yeah, and if we have, L stochastic variables, okay, we can also do this. And this is another method, an early one that we have, and this is related to the warped phase transformation. And again, if we have, heat equation as an example, and assume we have A of Z, okay, as our diffusion coefficient, but now Z is the stochastic variable, and now we have a warped phase-like transformation where instead of, e to the power minus, P, it's, minus A of Z, okay, P. And now if you ask what equation this, W, okay, function obeys, now the stochastic term actually disappears. Okay, and now we can actually simulate this and compute the ensemble average, okay, directly. Okay, and we also have quantum algorithms for those. And finally, I won't, say any details about this, but you can, come and ask us later. So, how about nonlinear ODEs and PDEs? Okay, because everything I mentioned here is linear, and that's because Schrödinger's equation is linear. Okay, so if you have a nonlinear equation, then you should have a way of turning, right, your nonlinear equations into linear equations before we can apply our method. So two examples of these. So for those of you who work in control theory, you're very interested in Hamilton-Jacobi, equations. And for Hamilton-Jacobi-like equations, for hyperbolic nonlinear equations, then there is a method of adding some dimensions to make them completely linear. Okay, and in fact, if you have nonlinear Hamilton-Jacobi equations, you need to add in twice the dimension roughly until it becomes a linear Liouville-like PDE. Okay, and if you had m initial conditions, you can actually make it into a Liouville equation with a single initial condition. And once we have that PDE, then we can actually put this into a quantum algorithm and actually output observables. And what happens when you have more general PDEs? Well, we can discretize these into systems of ODEs, and we know that for you guys who work on particle methods, it's easy to see how if you have a dynamical system, with lots of particles, then if you look at the probability distribution, then that obeys a linear PDE. Okay, even though your particles, they actually obey nonlinear ODEs. Okay, so we can do this, but actually this is not so efficient. Okay, so we don't get much quantum advantage actually out of this. Okay, so the basic message, in all this program of using quantum systems to simulate our PDEs is that whenever we have some problems that we want to deal with, we realize we actually need to find methods where we increase the dimension, not by very much, by a little bit, and we can actually solve lots of problems, with, on these quantum devices, that don't have this cursor dimensionality. And this is like a small summary, of the work we've been doing the last couple of years. So on linear PDEs, non-autonomous systems, uncertain PDEs, nonlinear PDEs, systems on nonlinear ODEs, certain boundary conditions, and we've recently also been doing some explicit circuits for these, so that later we hope to share with you an open source kind of program where you can actually use it yourself and try it out and actually be able to simulate these. We can also use these for linear algebra, ground state, and thermal state preparation, ones as well. So if you want to ask me about that later, you can. And thank you, and welcome to visit us in Jiao.
Thank you, Nana. Very interesting talk. So, are there questions or comments? Yes, right.
So when we do simulation of PDEs, a lot of time we want to see what the state is a few times, let's say for controlling it or something like that. But in this case, if you observe it, it will collapse, right? Is there a way to go around this?
This is a generic problem for all quantum algorithms that you can't really interrupt. Like in between to see. So for, usually what we do, at least in the first stages when we're performing experiments and these things, we can actually try, simulate, classically, what happens. And then, so using, classical control for quantum problems, right? So that, because this is what, when you're doing any kind of experiment, that's what you need to do anyway. So we're really treating this on, at the experimental stage, right, rather than the computational stage as to, how we would error correct, on its own. But people do, so for, discrete systems, people do work on error correction protocols, for these, where, you make partial kind of measurements, or what they call, mid-circuit measurements, and then you can, there are things you can do. But at this stage, we're not thinking about that. Yeah.
For a specific PDE, you have to actually design the system to have that multi-dimensional equation. Do you think there's a way to split it up into different systems and approximate it?
Oh yeah. So of course you can. Yeah. But the idea is that we want to start, as simply as possible, because actually the more systems you have, the more complicated actually the controls become, right? So and the idea here is that before these qubit, type of systems, or, these inhomogeneous systems where you have, or heterogeneous systems coming in, we want to demonstrate there are interesting PDEs you can simulate even on the simpler systems. But of course, if the simpler systems don't work, then, later on we want to go to these hybrids. Yeah. Yes, sir? Oh, actually, every quantum system are actually, in fact, qubits, right? There are no qubits, actually, in nature, right? We make them qubits, right? And this is, similar to, in classical information, 0 and 1 doesn't really exist, right? Even in our brains, when we think about zeros and ones, these are analog signals, right? On neural networks, you guys who work with machine learning, right? Also, there's nothing digital. I mean, in the end, you have an analog signal, and then you have to select, okay? If it goes to 0 or 1, okay? So, and this is how, so people try very hard to take, naturally continuous systems and make them discrete, because, as we do arithmetic and things like that, we like to think in a discrete way, right? But we're arguing that for problems like PDEs, which are naturally continuous, it makes more sense, at least at the beginning, right, to use, natural continuous systems. Because actually controlling them, controlling quantum systems is very difficult. And to make the discrete versions, as well as making them all coordinate in such a, very complicated way, and you have to use millions of gates, actually, even with the simplest PDEs. So with a heat equation, for example, you need millions of these gates. But whereas, with this type of method, we just need one, basically, but, controlled in a nice way. Right, and that's the comparison.
Okay, thank you again.
No, thank you.